So if we define this Py bar, tau A is greater than tau boundary of M, and HA bar of X and Y, so this becomes HAM of Y, 1 plus order of N over M for D greater than 3. And for D equal to 2, it's just HAM of Y, 1 plus order of N over M, Ln of M over N. And the theorem says that limit of HA, X and Y is just, of course, X comes from infinity. This is just the limit of HA M of Y, and this is HA of Y. This is a very important concept, and I will show you that you can say that this is just the escape from A, but you should normalize it with capacity of A. And I will define what are capacities and what are escaping probabilities. So escaping probability, we have A. So the escaping probability, sometimes you escape from A. So escaping probability, if we start from X, is the probability of tau A is infinity, which is the limit of tau A is greater than some variable that we have defined this before. It's just tau of Cm. Those things that I told you, CMs, those sets that are evolving, and the capacity that we see in many different theorems is just the escaping, the summation over escaping probabilities. So in the previous theorem, we can say that HA of X is just escaping probability divided by capacity of A. And of course, capacities are a little bit similar to what we say in the theory of electrical networks, but we don't need to talk about electrical systems anymore. Just think about probability. An important proposition is that if A is a subset of Cn and X is on the boundary, then the probability that tau A is less than infinity is equivalent to 2 minus the capacity of A. Now it is time to relate escaping probability and the green function. Of course, they may seem very intuitive, but imagine that you have a set A and a set B. So when the green function between X and green function of GB of X and Y is high, it means that the frequency that visits Y is high. So from here we may go to A, and then we may go outside. But let me just start the theorem. The proposition says that if A is a subset of Z and tau is the infimum of J, that Sj is in A, and tau bar is the infimum of J, that Sj is A, the proposition is looks very trivial, looks very intuitive and easy to understand, but we just want to use some interesting Markov properties as usual. So I give you the proof. So it says that if this A is a subset of ZD, then the probability, if we start from X, that tau bar is less than eta, this means that escape is hard. The proposition says that this is related to green function times the probability that tau is greater than eta. So this means that escape is easy. And this says this is the green function. Of course, stopped green function, and because it is GB of x and y. And so now you understand what is this. So when escape is hard, it depends on first how easy it is to visit A, what is the frequency, and also it depends when you enter A, then you should go out. It depends on that. So it doesn't have any physical intuition, just it may look familiar with if you are familiar with the green function. And so the proof is like this. We use the technique of last exit decomposition. So you can always define new stopping times and work on Markov property. And so let sigma to be the supremum of J that Sj is in A and J is less than eta. Then we can say the probability that tau bar is less than eta is just the summation over J of Px sigma J. So this means this. And then we can say it depends on y as well, because the probability that not only sigma could be J, but at any time Sj could be y. So y varies inside A. Now just we use Markov property. Just use Markov property and we say that this is equal to the probability that Sj is y and J is less than eta and Sk is not in A. But your K could vary. The lower bound of that is J, but it cannot go more than eta. So this is the way that we use the Markov property. And this is just, if you simplify this, this is just the probability that Sj is equal to y and J is less than eta times the probability starting from y. So first you go from x and then we start from y that tau is greater than eta. So here escape is easy when it's starting at A. And so we can say that the probability that tau bar is less than eta is just the probability that tau is greater than eta times J from 0 to infinity, the probability that Sj is y and J is less than equal to eta. But look, this is just the definition of green function, GB, x, and y. And then if you multiply, so this comes here, the probability that tau is greater than y, then eta, and so summation is as usual. So we have proved this theorem. So I want to talk about generating functions and their applications. So in probability theory, there is a technique known as, of course, we have generating functions, and then we have probability generating functions, we have characteristic functions, we we have cumulant log of that. So we have moment generating functions, we have characteristic functions. So all of these things, the intuition behind all of these things is that we want to use weak convergence. We want to see if because as you know, there are many different notions of convergence. Convergence in distribution, convergence in probability, convergence in many different convergence. And you can also define your own concept of convergence. And so, for example, when we talk about the moment generating functions, mx of t, it is the expectation of e to the tx. And why it is important for me? Because e to the e is just write the Taylor series, and you will see what happens. 2 plus tn x n factorial. And so the moment generating function is like 1 plus tm1 plus t2. So it gives you all of the information about the moments, especially if you just differentiate generating function I times with respect to t, and just let these t equal to 0, and then you get the ith moment. Isn't it beautiful? And so because a distribution and is a very complicated function, and so different moments usually talks about, for example, how steep they are, and so describing this complicated function is hard. But if you just let's say code it with some functions such as characteristic function, it's like the fingerprint of your fingers, and so they are unique. So if they converge to each other, then the random variables are converging to each other. And we use this technique, for example, in large deviation theory that I will talk about in the next 10 lectures, is all about this. It's a great way of using the weak convergence. And so I will talk. But first, we should start from generating function, which is a little bit more basic than all of these moment generating functions and characteristic functions, which is complex functions. And but generating functions has other applications as well beyond the important usage of weak convergence. For example, generating functions, it has applications. For example, sum of independent random variables, it has application in branching process, renewal theory. And how do we study distributions? And the answer is transformations. Probability generating function of discrete random variable, or moment generating function of a general random variable, or characteristic function of a general random variable. So continuity theorem allows us to use characteristic function in studying limits of random variables, for example. So one way to store I from 1, 2, 3. Assume that you are a machine learning engineer. How do you store a sequence? A way is to just wrap it up in a generating function. We call it generating function, which is, so these are coded like this. So if you just know this, then you know many of these informations. It's like that's one of the reasons that I like zeta function and Riemann hypothesis and those things, and holomorphic dynamics, conformal mappings, and those things. And of course, Abel is a mathematician that I really like because he's a person between pure mathematics and applied mathematics. So let's get back to AI. AI is just, you can say that this is the i's derivative and over I factorial. And now we can reconstruct like this. Like a Taylor series, that if you remember Taylor series f of a from high school, this is just like this, 2 factorial. And for example, you know from high school that this is just summation from xn, or if binomial series, you know that this is n from 0 to infinity, k from 1 to n, alpha minus k plus 1 over kxn. And so the generating function, for example, could be, an interesting case is the cosine of theta plus I sine of theta to the n, Sn. This is equal to 1 over 1 minus s times cosine of theta plus I sine of theta. So the probability generating function of a random variable is defined to be the generating function of its probability mass functions. So g of s is expectation of s to the x. So we can say si probability that x is equal to I, and this is s to the I f of I. So what is important, if x is non-negative integer and s is less than 1, so we can say that gx converges. This one, if this is less than 1, we can say g converges. And an example is Bernoulli variables. For example, there are some distributions like Bernoulli, Poisson, that you should calculate many of these things, like generating functions. You should calculate the rate function if you are working a large deviation. You should see, for example, I will talk about the rate function of Poisson or Bernoulli, but in the context of large deviation, because now I want to talk about generating functions. Our focus is on generating function. So I should control my temptation to talk about some other stuff in mathematics. So let's say this is s to the x for Bernoulli. You know that p of x equal to 1 is p, and p of x equal to 0 is q, which is 1 minus p. And so the generating function is 1 minus p plus ps. This is for Bernoulli variable. For geometric distribution, if x is geometrically distributed with parameter p, so that p of x equal to k is equal to p times 1 minus p to the k minus 1, then the generating function, in other words, e expectation of s to the x, is just k from 1 to infinity sk p times 1 minus p to the k minus 1, which is ps over 1 minus s 1 minus p. For the Poisson distribution, if x is a Poisson distributed with parameter lambda, then g of s is expectation of s of x